Okay, the next topic we're going to cover is the twin paradox. And this is a commonly described, how do you say, maybe a misrepresentation of what special relativity does, so that to make things look like the special relativity results in a paradox, when actually it does not result in a paradox. It just results in the relativity of simultaneity, which if you're not prepared to accept, then it seems like a paradox. But anyway, the idea is that we have, in the description here, we have somebody going at this guy's speedo travels away at 95% of the speed of light, and after 7.5 years, he gets homesick and returns back at 95% of the speed of light. The time dilation factor, which can be calculated as gamma equals 1 over square root of 1 minus v over of 0.95 squared, or the hyperbolic cosine of the hyperbolic arctangent of 0.95, comes out to be 3.202. So while speedo ages 13 years, go slow ages 42 years. Now, a space-time diagram of this situation looks like this, and the go slow here, let's see, age is 42 years, so 21 years. 21 years for both of these parts, and then speedo ages, what is it, 13 years. Okay, so that's all well and good. But when you come down here and look at these diagrams, what do things look like from speedo's perspective? And speedo ages 13 years here. So how long must go slow age is going to be 13 divided by 3.202. So go slow ages 4.1 years during this part of the journey and 4.1 years during this part of the journey. So what's going on here? What's going on here is that I've got this event A and this event C here, and I'll call this event B here. And what we're actually looking at is that event A is way down here, event C is way up here, and this is some desynchronization going on. So go slow ages 4.1 years here, 4.1 years here, and what is 42 minus 8.2? He ages 33.8 years here. But let me go ahead and do a little bit more than that, because I want to show you the whole space-time diagram rather than just these two parts of it. Okay, so here's the space-time diagram I've set up. We have event 0, which is down here. It is 20 light years distant at a time of 20 light years ago. The next one, or well, is it 20 light years ago? No, it's 21 light years ago, because it's going to take him 20 light years to get to where he's going, or 20 years to get to where he's going. And this one also is 21 years in the future, 20 light years away. That one is over here. And then we've got this event, which is like here at the origin. So this is where he turns around. I've put in the Lorentz transformation equations, which I put in their hyperbolic form. Just giving the value of xabel, or the Lorentz transform for the x coordinate and the Lorentz transform for the t coordinate, and then I've put those two together so that I get a point with both the x and t coordinate. And this is based on the rapidity, so I'm going to actually have the rapidity calculated from the velocity. I'm allowing the velocity to go from negative 0.95 to positive 0.95. And then I'm just drawing a polygon of those 3 points so that I can see that the three paths. And so what I'm going to do now, this is the this is from the point of view of the Earth reference frame, and you can see that the Earth's or go slow's reference frame, and so you can see that go slow's world line is vertical there. I'm going to go for the outbound journey, which means setting the velocity to 0.95. And now we can zoom in on this, and we see what we had, that Speedo is going for about 7.5 years here. And you can see that this amount of time experienced by go slow is, it actually ends up being about 4.1 years. So actually let me put that point in our diagram. But first let's make some corrections. This is 7.5, because added together that gives you 13 years, which makes this 10.5, and these are going to be 2.05. And so I've made that I've implemented those points by adding 2.05 to the time coordinate of e sub naught. I've added 2.05 or subtracted 2.05 from the time coordinate of e sub 2. So we've got an A, B, C there. And you can see as I change the velocity that B becomes simultaneous with our turnaround event at when the velocity is 0 from the Earth's point of view. C becomes simultaneous with the turnaround event on the return journey. So basically, during the time of acceleration, the person here is observing is very quickly would very quickly be observing all of the events, not actually observing ABC, because he's not actually observing those events. He's but they become, it changes the slant of the simultaneity line. So those events are in some sense just skipped as you go from positive 95C, 0.95C to negative 0.95C. So that is essentially the explanation for, or a part of the explanation for the twin paradox. Another visual we can use to get an idea of this, kind of the resolution of the twin paradox, is look at, okay, so if the Earth is, let me come back here, we had, okay, the Earth started from from Speedo's point of view moving to the left, right? So the Earth's clocks would have been ticking tick, 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 tick. And then when the Earth turned around, it was moving to the right. So its clock is going tick, 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 etc. Okay, so that is the idea of that being that it's actually slowed down. The clocks are slowed down. But look again and see where the tick marks actually pass the world line of the traveling twin. Here is how the clocks are ticking then. Tick, 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 tick. That is actually sped up from the reference frame of the traveling clock. It's he'd be looking at a different group of, or each of these ticks occurs on a different clock, but it is still that the clocks are ticking faster. Then when he comes back again, they're ticking faster. Tick, 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 tick. So if he uses, instead of looking at some single distant clock, he looks at the clock that is adjacent to him, and then the traveling twin is always seeing those clocks as a group going at a faster rate than his own. Now, just to give this demonstration a little bit more, I don't know, visualization help, I decided to throw in a couple of hyperbolas here, so you can see how each of those events A, B, and C are constrained to hyperbolas. A and C are on the same hyperbola because both A and C are events that are seen to be simultaneous with this event over here at the origin, depending only on the velocity of the observer. Either any event on that hyperbola can be seen as simultaneous with this point. Actually, any event on this hyperbola can also be seen as simultaneous with the observer over here, or with this observation event over here, or the acceleration event, I mean. So to summarize, speedo goes out at 95% of the speed of light, experiencing 7.5 years, and he sees, well, in his reference frame, 2.05 years pass for go slow. Meanwhile, go slow sees him travel that same 7.5 years, but he experiences 10.5 years. And the reason that that is possible, that this could be 2.05 years and this could be 10.5 years, is because they're measuring the time between this event, or two different events, 0 to A and 0 to B. And then on the way home, again, speedo sees 7.5 years. Go slow experiences, depending on whether you look at it from go slow's point of view, if it's from go slow's point of view, he experiences 10.5 years. If you look at it from speedo's point of view, he only experiences 2.05 years. But again, go slow is measuring the time from event B to event let's call it E2, and speedo is measuring the time between event C and E2. Speedo's reference frame is a little bit harder to kind of describe with a single spacetime diagram, but you see here that he sees this event A kind of swing down on hyperbolic path down to here, and event C also swings down on the same hyperbolic path. So I'll make that a little bit easier to visualize by giving you an animation of that swinging.